All right, so like I said, this section is on isosceles triangle theorem, which we have talked about like what an isosceles triangle is, but we haven't quite like fully talked about the isosceles triangle theorem. So we have defined isosceles triangle as a triangle that has at least two congruent sides. So we did a little bit of that at the beginning of this unit in 4.1. And so this section is all about isosceles triangles. So the isosceles triangle theorem, the actual theorem, states that if two sides of a triangle are congruent, then the angles opposite those sides are congruent. I think I did maybe mention this before when we were going over like the 4.2 homework, I think. But so if I gave you something like this, so pretend this isn't here. If I gave you that these two sides are the same, so if you know this, you can conclude this, that A is congruent to C because A is opposite BC and C is opposite C. So like these two are equal. So anytime you're given a triangle where two sides are the same, you could mark that the two angles are the same that are opposite those sides. And the reason for that is isosceles triangle theorem. So we use this in proofs, and we also use this to solve like more algebraic type problems. So I'm going to go over a quick example like that here. This is actually, as I was going over this example last class, I realized it was a little easier than I thought it was going to be, but you'll see. I'll go over another one on the practice later, one of the odd ones. So we're given that this angle is 68, and then you're given that these two sides are the same. So because of the isosceles triangle theorem, I could mark that these two are congruent. And so to find it, we could just subtract 68 from 180 and then divide by 2, right? Because these are equal. So it's going to be 56. So this is 56 and this is 56. And then you can keep going, like these are vertical. So then this would be 56. And then over here in this triangle, it's another isosceles triangle. So these two sides are the same. So I could mark that these two angles are the same because of the isosceles triangle theorem. So if this one's 56, so is this one. And then I could add these and subtract from 180 to find this one. So these two triangles ended up being congruent, which I didn't want to happen. That's why it was like a little bit easier than I thought, but that's okay. So then that one ends up being 68, because if you add 56 and 56, you get 112, and then subtract from 180, you'll get 68. So there's just one example. In my last class, they asked for more examples, so I went over some of the odds on one of the papers you're doing later. So I can do the same for you if you guys are interested. Okay, so there's one where you're just like finding angles using the isosceles triangles. And then this example down here is a proof that ends up using isosceles triangle theorem. So now from now on, when you're doing proofs, isosceles triangle theorem and then the converse, which we'll talk about on the back, these are like fair game now to be used in a proof. So you have to remember to look for it. So let's first restate the given here. We're given that CD is congruent to CG. And DE is congruent to GF. Which they already marked for you in the picture. If the given is not marked in the picture, you should always mark it, but it's already done for you here. And so let's take a look at what we're trying to prove here. We're trying to prove CE, this one, is congruent to CF, this one. So notice that CE and CF are segments. And so that means that we're going to have to try to show that some triangles are congruent first, the triangles that they're in. So do you see how CE and CF are part of these triangles, like this one and this one? And those two triangles that I just like shaded in, we already have two sides that are the same. So we're almost there, right? We just need a little bit more information. So if I'm going to highlight like this big triangle. So isosceles triangle theorem and its converse on the back, they're usually used in like when you have a picture like this, kind of like look at the big triangle, and then that's when you end up using one of these theorems. So see how if you look at this big triangle, you could even redraw it if you needed to. Right? That's CD and CG. So if two sides are the same, two angles are the same, right? So then I could mark D and G as congruent. And that would be because of the isosceles triangle theorem. And then once I do that, now the triangles will be congruent by side angle side. So we'll get to that in a second. But first, let's state rather, I already marked it, that D and G are congruent, and that's by isosceles triangle theorem. So angle D is congruent to angle G. And that's isosceles triangle theorem. Okay. And that was because we had that triangle with two sides that were the same. So we were able to mark that two angles were the same. The angles opposite those sides. So now if you look at the triangles that I shaded in, you can see that we have a side, an angle, and a side marked over here. And then over here, a side, an angle, and a side. So do you guys see how we have side, angle, side in both triangles? Now keep in mind that when you're determining like why the triangles are congruent, the angle that has to match up in both of the triangles. I had some kids for ACLAB this week, and some of them have like a revelation that like, oh, wait a second, they actually have to match, or like the angle has to be in between the two sides. That's super important. So this would be what side, angle, side looks like. So now to do the triangle congruence statement, the order has to match, remember? So if I go from C to D to E, down the side with one tick mark, down the side with two, it would be C, G, F that would match. And that's not the only statement, that's just what I just made up and chose. So C, D, E, whatever you pick for the first one, you have to match it up for the second one. It would be congruent to triangle CGF. And that's side, angle, side. Okay, now that I have the triangles are congruent, now all their corresponding parts are congruent. So now I could say that CE is congruent to CF. And that would be CPCTC. So there's our first proof using that theorem. Do we have any questions about anything that I did? No. Okay, so let's go to the second page then. The second page talks about the converse of the isosceles triangle theorem. So if you guys remember earlier in the year, we learned about what a converse was. A converse is when you flip the if in the then of a theorem. So just to recap, the isosceles triangle theorem says if two sides are congruent, then the angles are congruent. So we're going to flip that. The converse says if two angles of a triangle are congruent, so this part now is coming first, then the sides opposite those angles are congruent. So if you take a look at this right here, so this would be like, say I gave you this picture with two angles that are the same, you could now mark that these two sides are the same, the sides opposite those angles. So if I gave you P was congruent to R, you could conclude that PQ is congruent to QR. And the reason for that, so say you did that in a proof, the reason would be the converse of the isosceles triangle theorem. I also gave a more like algebraic type example for this before we do the proof. So see how we're given that 50 and 50, like those are congruent. So that means those are the base angles of this isosceles triangle, and it's the ones that are opposite it that are congruent, so this and this. So then we don't need this 4x plus 16. In this example, we would just do 3x plus 13 equals 5x plus 2, and then you would solve. So if you subtract 3x, and then subtract 2, so that's 11 equals 2x, and then x is 5.5. So when you have to do ones with algebra or just with like angle measures, just figure out if you're given two angles that are the same, figure out which two sides are the same, and then solve. Okay, so there's that one. And then we're going to do another proof. This one uses the converse of the isosceles triangle theorem. Although last period when I was going over this one, I found another way to do it without using the converse of the isosceles triangle theorem. So I'm going to ignore that method. We're going to just do the one that uses the converse, and then you can see it. Okay, so here's the proof. We're given that 1 is congruent to 2. And 3 is congruent to 4. So restate the given, let's mark it too. So 1 and 2, and then 3 and 4. Okay, so that's what we have so far. And then let's take a look at what we're trying to prove. We're trying to prove that PT is congruent to LX. Those two. So in order to show that PT and LX are congruent, we're going to have to show that the triangles that they're in are congruent, and then we can do CP/CTC. So here's where your options are kind of opened up, because they're in, those two segments are in kind of a lot of triangles. They're in these little ones, PTR and LXR. They're in like PTL and LXP. They're in PTX and LTX. So you have some options here. Really only 2 of those options would work, because the like this PTL and LXP, like these 2 triangles don't have anything marked in them. So like this is not this whole angle P here, or LPT. So really your only options are these little ones, or PTX and LXT. I'm going to do the little ones because those are the ones that require the converse, but we could talk about the other way to do it later if you guys want. So anyway, take a look at 3 and 4. Do we see how 3 and 4 are in the same triangle? 1 and 2 are not. 1 and 2 are in different triangles, but 3 and 4 are in the same triangle, TRX. And so when you have 2 angles that are the same in one triangle, 2 sides are the same, right? And that's the converse of the isosceles triangle theorem. So if 3 is congruent to 4, that would mean that TR is congruent to RX. And like I said, that's the converse of the isosceles triangle theorem. Given 2 angles are the same, you are marking 2 sides that are the same. So that's what I'm going to do next, is say that TR is congruent to RX, and that's converse of isosceles triangle theorem. Oops, let me zoom out a little bit here. So now we're one step closer to proving that these smaller triangles are congruent, because now we have 1 pair of angles and 1 pair of sides. Do we see what else we could mark here to show these triangles are congruent, the ones I just shaded in? What else could we mark? Vertical angles. Thanks, Anthony. Good. So we could mark this one and this one. You can't really see, I guess. Let me zoom in a little bit. I did 3 arcs here. So those 2 angles are congruent because they're vertical. We have to name them with 3 letters. So we can say PRT, angle PRT is congruent to angle LRX. And that would be vertical angles theorem. Okay, so now that I have that, now the triangles would be congruent. What would the triangles be congruent by? Good, Aiden. Angle, angle, side. So angle, angle, side, angle, angle, side. I noticed on the quiz from the other day, a lot of you mixed up angle, angle, side, and angle, side, angle. If these were going to be angle, side, angle, see if I can redraw this here. It would have to be this side, not this one. So see how it's angle, side, angle. The side has to be in between the 2 angles, versus this, the side is not between the 2 angles. So that's why it's angle, angle, side. So if you are still confused about that, I would definitely come for help. Already a lot of you revised that quiz from the other day, but if there were quite a few of you actually who didn't really do so hot. So if you'd like to revise, you can come for ACLAB. Just let me know. Okay, anyway, so let's do a triangle congruent statement. PRT is congruent to triangle LRX. And then the reason for that, like we said, is angle, angle, side. Good. And then now we can go to the last part, which is PT is congruent to LX, because those are corresponding parts of those congruent triangles. So PT congruent to LX, and then that would be CPCTC. And that's it. So I feel like I should mention the other way, just so you, I don't know, maybe some of you saw it, but the other way would use PT, oops, this doesn't work, PTX and LTX. So you could say that TX is congruent to itself, and then you'd have like C1 and 3 are in PTX and 2 and 4 are in LTX. So you could do reflexive and say TX is congruent to itself. It's a shared side, and then it would be angle side. So that would have been another way. Anyway, okay, so that's it. I'm going to stop this recording and then